So, we are discussing emission and absorption processes. So, the difference in energy, if it comes out as a form of radiation or a light or something like that, it is emission. But if there is no change, no radiation change, but only the amount of energy is absorbed, then it is absorption. So, the process of monitoring the change in the electromagnetic radiation in the absorption is the amount of energy in one case. In the case of emission, we have to measure the wavelength of the radiation that is coming out, that is emitted. So, what are the different types of emission of radiation? This we have already covered in my last slide. So, when excited atoms, ions or molecules, they return to the ground state, excess energy is released as heat or in the form of photons. Excitation can be brought about by bombardment, supplying heat, electrons, etc. And we get ultraviolet, visible, infrared, these are the absorption processes. UV absorption, visible absorption, infrared absorption, these are all very familiar to us in terms of absorption, because whenever you see a colored glass or something like that, you will see only the color of the glass, like wearing a goggle. If you are wearing a blue goggle, you will see everything blue. That means all other substance, all other colors are absorbed. So, absorption is a phenomenon known to all of us. If you wear a green goggle, you will be seeing everything in green color. So, that means green color is emitted and all other colors are absorbed by the green colored goggle. So, goggle is the medium. So, same thing happens with whenever material goes to higher energy state using ultraviolet, visible or infrared. So, these are all absorption processes. And a beam of electromagnetic radiation, if it is emitted from what you have supplied, then it is known as fluorescence. That means radiation entering is one wavelength, radiation coming out is another wavelength. In the case of absorption, what goes in comes, same thing comes out. And exothermic chemical reaction means here there is no energy supply as such, but from chemical reaction the outcome is in the form of radiation, that is known as chemiluminescence. So, what are the different types of spectra we expect in molecular absorption? So, here I have listed, one is they are line spectra and another is band spectra. So, basically what happens is the spectra, what does it represent? It represents the function of the relative power of the emitted radiation with respect to wavelength or frequency. That means, I will plot the interaction, the result of interaction in the form of electromagnetic radiation as one axis and absorption or emission as another axis, percent absorption, percent emission, etc. And these are in different components. One is lines, one is bands and another is a continuum spectrum. So, there are three types of absorption type spectra. One is line spectra, another is band spectra and another is continuum spectra. So, what is a line spectra? Line spectra are a series of well defined peaks. That means, they are so sharp that they look like dark lines on a photographic plate. So, band spectrum consists of several groups of closely related spaced, but for example, I can draw it here. If I have a spectrum like this, I will see a peak like this, different line spectra. On a photographic plate, all these things will look dark lines. And in band spectra, what I see is a peak like this. Something like this. And in a continuum spectrum, what I see is a continuous color merging from one into another, or it may be any other mixture, that is slowly changing from one to another, or it may be simple yellow color or brown color, etc. This is the band spectra, this is continuum spectrum. Okay. So, in line spectra, the atomic particles are preferably obtained in the gas phase. That means, if I take material in the form of a gas, pass the radiation through the gas, I get line spectra. That means, I put a photographic plate at the other end, I get different dark lines, that is line spectra. So, basically the typical widths of line spectra, actually they are also peaks only, because nothing is actually a simple line spectra. As I have explained to you, any monochromatic slate will give you a group of frequencies, and the width of the width, if it is very small, you will see it only as a line spectra. So, the typical width of a line spectra is of the order of about 10 raised to minus 5 nanometers or 10 raised to minus 4 angstrom units. That is why you will see them only as a single line, whereas because our eyes are not sensitive enough to see the full band. Now, X-ray line spectra is another line spectra produced by the transition of the electrons, and they are produced by the transitions of the electrons to the innermost orbitals. Now, you imagine that we have an atom, electron is there at the top, and then it falls to the ground floor. Then it falls to the lower energy level. So, atomic level, at the stage of atomic level, X-ray lines are produced. So, it is not a molecular spectra, but it is atomic spectra. So, it is characteristic of the element, but not of the molecule or a compound. That is special about X-ray. Then the band spectra. Now, we discuss about band spectra. So, what type of compounds normally generate band spectra? So, if we look at it, as I have explained to you, that if we have a group of molecules like OH, COH, aldehydes, ketones, etc., 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 if I have the radiation falling on them, then I get radicals, and small molecules usually exhibit band spectra. They do not exhibit line spectra, because the bandwidth is slightly more, and our human eye is sensitive enough to see a Gaussian curve there. So, a Gaussian curve is typically characterized by a peak which falls uniformly on both sides. So, whenever I plot the energy and excitation process, the band spectra will give me a Gaussian curve. Not necessarily Gaussian curve all the time, but 99% of the time you will be seeing a Gaussian curve in band spectra. So, the lifetime, and these are all associated with the vibrational energy levels, not the electronic energy levels. The lifetime of vibrational energy state is approximately 10 raised to minus 15 seconds. within that time the whole excitation and emission occurs. Whereas, for an electronic transition, it is 10 raised to minus 8 seconds. You can imagine the difference, almost 10 raised to minus 7 seconds is the difference. That means, the vibrational energy changes are 10 raised to 7 times faster than the electronic transitions. Therefore, transition always occurs from the lowest vibrational energy of the excited state to any of the vibrational energy of the ground state or excited state. This I have already explained to you using the analogy of kicking a football from ground floor to higher floors with number of steps, and each step is associated with number of smaller steps, that is they which represent floors represent electronic energy level, steps represent the vibrational energy level, and small cuttings on the steps will represent rotational energy level. So, the loss of energy from vibrational energy levels to the lowest vibrational energy, the loss of energy, see generally what happens is whenever I have the energy levels are above the electronic levels. So, the part of the energy is slowly lost until it comes to the 0 level of the excited state. So, if it is higher than in the excited state, if the vibrational energy is not 0, it may be 3 or 4 etc. So, slowly they will lose a little bit of energy, come to the ground state, from there quantum jump to the lower energy state. So, but even the transition from one vibrational to another vibrational level and one rotational level to another rotational level, they also follow the quantum mechanical rules. So, it is nothing continuous from there. So, the lowest energy it occurs through the how the energy loss occurs. The energy loss in vibration occurs due to collision of the solvent molecules, collision with other molecules. So, this energy loss is not usually represented as a absorption peak. So, now we talk about continuous spectra. In continuous spectra, the radiation from the black body when heated to incandescence is what you see as a continuum spectrum. So, anything heated, if you go to your blacksmith and when he takes metal and keeps on heating it, and then before he beats it, at that stage whatever radiation comes out when it is heated to red hot or white hot, we call it at the still higher temperature, it becomes white, and that is a continuous spectrum. The radiation coming out from a black body around 3000 to 4000 degrees centigrade, when it is heated, whatever comes out is a continuous spectrum. It is not a line spectrum, it is not a band spectrum. So, the energy peaks shift to shorter wavelengths with increasing temperature. This is again a very well known phenomenon defined as Wien's law, and heated solids are important sources of ultraviolet, visible and infrared, because it is a continuum spectra. So, if I want to generate electromagnetic radiation, what I should do is suppose I want UV, I want visible, I want infrared, or what I have to do is I just have to take a metal, heat it to incandescence, I will get all the UV, visible and infrared radiation from the metal. So, the three types of spectrum what we discussed are special, that is line spectra, band spectra and continuum spectra. Now, we talk about absorption of spectrum, absorption spectra. So, atoms, ions, molecules, they, as I have already explained to you, they absorb electromagnetic radiation, go to the excited state, according to laws of quantum mechanics. The energy difference corresponding to each excitation is unique for each species or group of atoms. This we have discussed number of times. So, how do you plot the energy difference? It is by plotting absorbance as a function of wavelength or frequency. So, absorption spectra normally differ from the very sharp peaks to smooth continuous curves like a Gaussian curve, depending on the physical state, complexity of the molecule and the environment of the sample. Suppose that I take the sample in a liquid state, then the same absorption spectra will be in the liquid state will be different from the gaseous state or in the solid state. So, this is a very important aspect, and it helps to know which state a substance is before we take the spectrum. So, the atomic spectra of an element results in only a few simple peaks, and excitation can occur only at electronic energy levels of the outermost or bonding electrons. You see it does not happen innermost electrons. Why? Because the innermost electrons are always satisfied with respect to quantum mechanical changes. Only the outermost electrons, they are the ones which undergo excitation, emission, absorption and all those things. So, the bonding electrons are the outermost electrons only. So, molecular absorption spectra are normally more complex, involving quantized vibrational and rotational energy levels. The energy of vibrational transition is definitely much more than rotational, and energy of excitation would be automatically higher than the vibrational energy levels. So, what we get actually is molecular absorption peaks involving electronic energy transitions. They are fairly broad, and owing to the presence of a number of vibrational and rotational energy levels associated with them. As a result, what happens is the spectrum of a compound consists of a number of closely spaced absorption lines that constitutes a broad smooth absorption band, giving the impression of a continuous spectrum. Basically, it is not. So, for example, the molecular absorption, what I was telling you is I wanted to show you a figure how it will appear as because the electrons are electrons, one electron may be here, another electron may be here. So, there will be a group of electrons which are appearing as a peak E and wavelength. So, this you can keep it, it shows as a simple peak, but the transmitted radiations are will always appear like this. Sometimes the absorbed energy is re-emitted as a radiation of lower frequency, that is fluorescence, and the energy changes occurring in the electrons and nuclei under strong magnetic field are studied by NMR or ESR, electron spin ray, but we are not going to study them. This is only part of the continuation of our discussion on the molecular absorption spectra. So, this brings us that in spite of all the things that we have discussed earlier, we will be continuing our discussion mainly in UV visible spectrophotometry and related aspects, that is turbidimetry and then fluorescence, nephelometry, etc. So, from now on our discussion will be mostly in UV visible spectrophotometry. Okay. So, to absorb radiation, a molecule must interact with the radiation within some time frame. This I have already explained to you that it is of the order of about 10 raised to minus 15 seconds. So, the exchange of energy normally occurs only by the interaction of potential energy component of the molecules, because the molecules are at very high are in a state of agitation, and the electrons are also in a state of agitation, and they can be represented as a vertical line in the energy diagram. So, the absorption bands occur only at definite values corresponding to the energy changes required to promote the electrons from one level to another. This we have already discussed. And UV visible absorption spectrophotometry is no more different than other absorption spectrum. Okay. So, when the solute molecule in the excited state loses its energy, that means a solute molecule takes up the absorption and goes to higher energy state, but there is no emission. So, after some time it loses its energy, it falls back to the ground state, and the solvent molecules absorb the additional energy that is released when it comes back to the ground state. At this point, the molecule returns to the ground state by means of radiationless processes. That means no radiation, but only the release of heat. That means the sample gets heated to a certain extent. So, the excess energy, what happens to this heat energy? The excess energy is transferred to other molecules in the medium. Suppose you are measuring a particular chemical and doing it in the aqueous medium. So, water molecules will be there. So, excess energy after absorption is transferred to water molecules. If you are doing it in a MIBK, methyl isobutyl ketone solvent, the excess energy will be transferred to MIBK solvents. If it is gaseous substances, the other gas molecules will pick up the extra energy of the absorption when the molecules come back to the ground state. So, this happens by normal collision, and kinetic theory takes care of it, and the excess energy to other vibrational and rotational all other modes is within the excited molecule. So, both these relaxation processes are accomplished by the loss of thermal energy, that is amount of heat lost to the medium. So, now that brings us to the molecular orbital theory. We have to discuss this a little bit before we proceed in our discussion on the molecular absorption spectrum. So, what actually we will be discussing is what happens when two molecules come and interact with each other. The two molecules, whenever two atoms react to form a compound, electrons from both atoms participate. That is understood. Two atoms are there, they come nearer, and the electrons of one atom will react with the nucleus, will be attracted by the nucleus of the other atom, gets attracted, and electron from the nucleus will be of one atom will be attracted by the electrons. So, when two atoms interact to form a compound, electrons of both atoms participate in the bond formation. So, as I was explaining to you, electrons of one atom will be attracted by the other nucleus, and nucleus of one atom will be attracted by the electrons of the other atom. So, whenever there is a chemical reaction, there is bond formation from the outermost electrons. This is understood, very simple. So, when the molecule forms, the electronic orbitals form molecular orbitals. So, we do not call them no more electronic orbitals, but we call them molecular orbitals. And in molecular orbitals, bonding electrons are associated with the molecule as a whole. I think most of you are familiar with single bond, double bond structures of several organic compounds and inorganic compounds, and this is what we are talking about. Whenever there is a reaction of carbon-carbon atom, there will be a sigma bond and then pi bond, double bonds will be there, triple bonds are also known, and these are all molecular orbitals. So, there is a change in the molecular sigma bond, bond energy. This is called as bonding orbital. Whenever a bond is formed, the electrons occupy an orbital called as bonding orbital, which represents the lowest energy state. So, correspondingly, an anti-bonding orbital also is formed, which are vacant in the ground state. Now, imagine I have two hydrogen atoms and I bring them nearer. So, there will be attraction between the electrons and there will be a bond, and this bond is the lowest level. Now, correspondingly there will be another level corresponding to this bonding orbital, there will be anti-bonding orbital at a higher state. So, at room temperature anti-bonding orbitals are all vacant. So, there is a possibility for the electrons, whenever I supply energy to the molecule, the electron may be excited to the anti-bonding orbital, still retain the molecular structure. So, this is what we normally expect whenever two molecules react with each other. There is a bonding orbital, but there is also a corresponding anti-bonding orbital which are normally vacant. So, a covalent bond, all these things are known to you now, because we know that a sigma bond, a covalent bond, ionic bond, we talk of all these things. A covalent bond is normally preferably present in most of the organic substances. So, we call them, they are formed by the combination of the s orbitals or p orbitals of the carbon atoms and several other atoms also. So, whenever there is a direct bond formation, we call them as sigma bond. If it is a single bond, we call it sigma bond, and if there is a double bond, one of them would be pi bond. So, in acetylene there is a one sigma bond and two pi bonds, triple bond it is. In ethylene there will be one sigma bond and one pi bond, so it is a double bond. In methane etc., there are only sigma bonds. So, we have to imagine at this stage that every sigma bond is having an anti-bonding orbital known as sigma star. Okay. A pi bond will be having an anti-bonding orbital, corresponding anti-bonding orbital, that is pi star. So, normally valence electrons not participating in chemical bonding are referred to as non-bonding electrons or n electrons. Sometimes what happens is, if you imagine a structure like ammonia, this is nitrogen, this is hydrogen, there is bond formation, but nitrogen is having 2 electrons in the extra which are not involved in bond formation. But if I form an ammonium ion, these 2 electrons also will be involved in bonding. So, these 2 electrons on the nitrogen are known as non-bonding electrons. So, what are the elements which have non-bonding electrons? These include nitrogen, oxygen, sulfur, halogen atoms and several other elements which are in the periodic table, but in general in organic substances we normally come across nitrogen, oxygen, sulfur and halogen atoms. So, all these atoms will be having non-bonding electrons or n electrons in their functional groups. That means, we have 3 types of electrons in a molecule. One is which is engaged in the formation of a sigma bond, engaged in the formation of a pi bond, plus there will be some extra electrons around the nitrogen or oxygen or sulfur or phosphorus or many other things, halogen atoms. Those electrons are not involved in bonding, but they can get excited to anti-bonding orbital. There is no guarantee that only the bonding electrons need to get excited to anti-bonding orbitals. Non-bonding electrons also can get excited to anti-bonding orbital and occupy them. So, whenever I take a substance which is having a compound like an element like nitrogen, oxygen, sulfur, the non-bonding electrons can also occupy the anti-bonding orbitals. So, that brings us to the shape of these orbitals. So, you can see here in this figure I have molecular orbital, here there is pi bonds and a molecular pi bond pi bond will look something like this, and anti-bonding orbital would be looking the other way around. That is, there will be the space, electronic cloud will be occupied by at higher energy level. These are the bonding orbitals. So, here I have an atom A and here I have p bond, and then molecular orbitals would be pi pi star. So, this would be the structure of the pi bond, anti-bonding orbital at the bottom. On the top I have a bonding orbital. So, all in all I have 4 possibilities in a given molecule. One is sigma bond, another is electrons occupying a sigma bond, electrons occupying a pi bond, and electrons occupying non-bonding electrons. These 3 are at the lower level. Okay. So, these 3 are occupying at the lower level, that is sigma, pi and n. Corresponding anti-bonding orbitals are pi star and sigma star. Obviously, sigma bonding is the lowest in energy level. So, corresponding anti-bonding orbitals would be highest, sigma star. So, next is pi, another corresponding anti-bonding orbital would be lower than the sigma star, sigma star. And then non-bonding electrons, there is no corresponding non-bonding anti-orbital. The non-bonding anti-orbitals can only go to pi star or sigma star. So, in essence what we have is the electronic transitions involved in ultraviolet and visible regions include sigma to sigma star, n to sigma star, n to pi star and pi to pi star, and their relative transition energies are shown here, which is sigma to sigma star is maximum energy, n to sigma star is the next higher energy, and still lower would be pi to pi star, and that would be greater than n to pi star. So, we will come back to this basically regarding the atomic absorption, the molecular absorption, bonding and other things in the next class, and we will be discussing more about the possible transitions of organic compounds that undergo these kind of changes, where the electrons are excited from bonding to non-bonding orbitals, how they can be used in our UV visible spectroscopy. So, thank you, have a nice day.